Hello, and welcome to our HEI's virtual workshop on health applications for satellite-derived air quality. This is session 2, Global Applications of Satellite-Derived Air Quality Data. We're really happy you're here. I'm Allison Patton, a senior scientist at HEI, and one of many people working on the team to bring us this workshop. The full program for the webinar series is available on at the URL on the slide and being posted into the chat. And we also welcome you to complete the pre-workshop survey at the link shown. If you have any questions for the roundtable discussion in the 4th session, we really look forward to hearing those in either the survey, or you can chat it to us, or you can email, however you feel is most convenient for you to get it to us. Now, before we begin the main portion of the webinar, there are a few housekeeping details. First, all attendees are muted and view only for the duration of the webinar. There will be a Q&A period after the presentations. You can submit the questions via the Q&A function at any time during the webinar. After each talk, there should be time for a few clarifying or short questions, but all others will be held for the larger discussion session at the end of the webinar period. If you are having any logistical difficulties, please contact us using the chat box. The webinar slides and video will be available in the coming weeks. Please check the HEI website for details. And the slides and recording for session 1 are already up. So if you missed that session, you can check it out later. And again, really, please tell us about your work on satellites, air quality, and health, or just what you're hoping to get out of this, this workshop if you haven't done any work in those areas before. For those of you who are new to HEI, we are an independent nonprofit corporation chartered to provide policy-relevant, high-quality, impartial science. We have joint funding from government and the worldwide motor vehicle industry, and occasionally also from private foundations. We fund research that is selected, conducted, overseen, and reviewed independently of HEI's sponsors. Additionally, the committee that identifies research topics and oversees studies is completely separate from the committee that reviews studies for publication. We also publish both positive and negative results, all of the important methods from the studies, so that there's a complete record of what was done. Finally, we don't take policy positions. Examples of several recent HEI studies that were published are on the slide. You can also find other publications on our website. The committee that selects our research and does strategic planning is the HEI Research Committee. So they're hosting this webinar to learn more about satellites and air quality and to think about where HEI might go next. From the research committee, we have 2 chairs of this workshop, Dr. Jeff Brook and Dr. Heather Holmes, and they're both here today. Now, so getting into the content of the workshop, there are 4 sessions in the workshop. This is the 2nd one. And we hope that you'll be able to join us for all of the sessions, or if not, just check out the videos and see what's going on and what you can learn or contribute. For today, we're focused on the global applications of satellite-derived air quality data. The session chairs are Dr. Eloise Marais from University College London and Dr. Kalpana Balakrishnan from the Sri Ramachandra Institute of Higher Education and Research in India. We're starting with some brief introductory remarks from Dr. Marais. Then we'll have 2 longer talks, one on satellite and ground monitoring data for monitoring of air quality, and another for satellite data for air quality exposure assessment and epidemiology. Then we'll have 3 examples of satellite data applications to air quality and health research from around the world. And finally, we'll end with the Q&A period, where we hope to answer some of the audience questions, as many as we can get to. So here are the speakers, chairs and speakers, and I'll next pass the mic to Dr. Marais to give some introductory remarks for the session today.
Excellent, thank you, Alison. I realize that I stand between you and our fabulous cohort of speakers, so I'll keep my opening remarks relatively brief. And just to remind everybody of a historical perspective of the satellite observations that have provided us with information about air quality, all the way from the global ozone monitoring instrument experiment that has a spatial resolution that's provides us with very broad regional information about air quality, all the way to the Tropomi instrument now that is widely used in part because of the very fine scales that it provides us, where we can start to understand borough and suburb scale air quality in particular in large cities. The other advantage of these satellite data products is that the individual instruments provide us with this really long record of information. And because these instruments have been in space longer than their anticipated lifetime, some of them for more than a decade, we can get this really long-term consistent record of information about air quality. And many researchers have pushed this beyond the limits by actually stitching together information about air quality from multiple instruments to really extend the record across the whole satellite data record. And of course, this data is provided at the range of user capabilities and also increasingly open access, just to enhance the amount of users who are making use of this data product to be able to better understand air quality across the world. And of course, something like this is a very familiar representation of the advantage of these space-based instruments, where we can look at a ground-based network and see that we have spatial data gaps, but also data access and quality gaps that stand in the way of understanding air quality across large swaths of the world. And so on the right-hand side, showing as an example the space-based observations of tropospheric column densities of NO2 from the Tropomi instrument, we can see that we can understand not only terrestrial air quality, but also air quality over oceans. And we'll see from presentations in today's session that researchers have combined these data products with surface observations, with numerical models, with statistical and gridding techniques to achieve even finer scales than the native resolution of these instruments, to be able to quantify air pollutant abundances, trends, and sources, as well as the impact these have on global health. And so, of course, the examples that we'll see are dominated by low Earth orbiting instruments, which provide us with one piece of information per day. And we're all very excited about the anticipated constellation of geostationary instruments that, although limited in the domain they sample, can provide us with hourly observations during daylight hours. And so the examples, the geostationary instruments included in this constellation include TEMPO over North America, Sentinel-4 over Europe, and a swath of North Africa and the Middle East, as well as the GEMS instrument, which is already in space, providing us with observations. And for those of us interested in air quality in regions not covered by those geostationary instruments, we still have a continuation of low Earth orbiting missions that will provide us with information where these geostationary instruments don't. And of course, there's examples of missions like the NASA Maya mission that we're all very excited about, because it's been designed with air quality and health communities. So it's specifically tailored to the end user's needs. And so in today's session, we're going to see a progression from the representativeness and usefulness of the satellite and ground-based data for monitoring air quality, to the use of satellite data for air quality exposure assessment, as well as epidemiology, and then examples of the application of this air quality and health data from various parts of the world, including India, Colombia, as well as South Africa. And so without further delay, I would like to introduce our first speaker, who is Fondoncolor, who's going to be telling us about the representativeness and usefulness of satellite and ground-based data for monitoring air quality. And Aaron is from Washington University in St. Louis, and you'll see his bio appear in the chat window of the Zoom window if you'd like to find more about his biographic information. Over to you, Aaron.
Thank you very much. One second. All right. Well, first off, I'd like to start by extending a sincere thank you to HEI, both for inviting me in, but perhaps more importantly, for organizing this whole workshop. It's really wonderful to be able to discuss and to reflect on the opportunities that satellite-based estimates have provided up until now. And it's also really exciting to look to the future and see where we can take this really valuable data set as we move forward. Major theme I really want to stress throughout this entire presentation is that the complementary nature of ground-based and satellite-based observations. For the part of ground-based observations, of course, probably familiar to many of you, these can provide locally accurate information with frequent and reliable sampling periods. But challenges really exist sometimes in how to interpret these location-specific observations in terms of a broader context. Two very simple examples I've given on the side here. We have two monitors potentially very well placed for certain applications. We have one here right over our traffic corridor. Really great data set if you're interested in traffic flow and the influence of that pollution, but potentially a real challenge to use if you're interested in pollution even as far away as those buildings you see in the background.
Aaron,
on the other, yeah.
Sorry to interrupt you. I wasn't sure if you were planning on sharing your screen.
I have not shared my screen. Yes, I am sorry. One moment.
Not a problem.
I thought I had done that. All right. My apologies. All right. So okay.
Excellent.
Sorry. My apologies for that. Okay. So as I was saying, we have these two monitors I was discussing that apparently no one could see. Really well placed for particular applications. On the right, one very much set up for a traffic corridor study. On the left, on the right here, then we have one that is well placed for a very different application, very obviously clearly in a forested region, probably a national park, likely representative of a very broad area, but presents its own challenges when trying to bring that into a more population assessment in terms of what that actually is telling us about air pollution for the population. Viewed more broadly, more globally, here I have a plot. This is akin to what was shown by Eloise just a moment ago. Here we have a plot of ground-based monitors that are relatively publicly available. These are more reference grade monitors, so a little bit more sparse than Eloise showed, but really giving an idea of where monitors are available pretty much at present around the world. And what really is striking this image, of course, is that North America and Europe and the eastern part of China, you have relatively dense monitors, of course, with lots of gaps in placement questions, but relatively good coverage. But for much of the rest of the world, there's essentially almost no high quality reference grade information available. An additional layer we can add on top of this, of course, is investigating what if you want to look further back in time. And so we take the same plot and sort of roll it back in time and say what was available between 2000 and 2005. What we see is in terms of a stable network, essentially North America provides at present the only stable long-term information on the ground of PM2.5 monitoring. Now, satellites offer, of course, an inherent complement to this information. Satellites, for their part, of course, are also observationally based, but what they can provide is incredible spatial coverage. And so if we look on the side here, here's an image taken of some wildfires over California from a few years ago. What you can really see is, of course, this fine detail that is available from the satellites from this space-borne view. They also provide, of course, a long, consistent time series with many of the instruments we're using for aerosol or for other species as well, really being available from around the turn of the millennium or even before, depending on the particular application. And you can see down below here in this plot, this is a figure of aerosol optical depth. We'll discuss that a bit more in a moment. What I really want you to walk away from with this is just the rich spatial information that is available from satellite. Of course, satellites do not directly measure PM2.5 mass, and this presents a challenge in many cases. Satellites rather retrieve the total column of aerosol from the Earth's surface up to space via a metric called the aerosol optical depth. Now, aerosol optical depth, for its part, is a measure of the light that's been extinguished from passing through the entire atmospheric column. But this has some inherent associations and rather intuitive associations with air quality. As you can see here, this is an image taken over China. And familiar to some of you, I'm sure, in terms of a high pollution day versus a low pollution day, the effect that has on visibility is quite dramatic. And so on a high PM day, it's really hard to see. It has that smoggy look that some of us might know. Now, satellites, of course, aren't viewing across the city. They're rather viewing from space down. So here we have an image below over the Indo-Gangetic Plain taken from the MODIS sensor. And what you can see is this large plume of pollution sitting over the Indo-Gangetic Plain with quite a lot of similarities in terms of that look to it compared to what we see across the city on a polluted day. And so what a satellite retrieval does then is it goes ahead and it interprets these images into this quantitative metric, this aerosol optical depth. And it does this using radiative transfer code. Essentially, it separates out from the image what was light that's bounced off the surface and come back up to be viewed versus that light which has come and interacted with aerosol and then is viewed by the satellite. One of the major challenges in doing this, of course, is surface reflectance term. This is a challenge for satellites, and this is one of the reasons there are so many different satellite retrievals out there, is different groups have sought really to address, to most effectively represent the surface under different conditions or using different sources of information. A very simple example of how this can look different in different conditions is shown here in the top right. You can see over oceans where it's relatively dark, it's very easy for your eye to pick out, where those aerosol are, but becomes more difficult over different land surfaces. And so a major focus of our group is often looking at these different retrievals and effectively trying to decide when it's best to use different retrievals under different conditions and bring those all together. Of course, even once you've done that, aerosol optical depth is again not PM 2.5. And a major challenge in using satellite observations for surface air quality is to relate these column values to surface concentrations. To meet this need for our part, our group uses a chemical transport model to relate these AODs to PM 2.5. Now, for those of you not familiar with CTMs, such as GSChem, these are essentially really complex computer codes that combine the equations that govern atmospheric chemistry and physics, and they combine these with assimilated meteorology and emissions, basically producing an entire simulated atmosphere, such as you see in this animation here. What I'd like you to draw from this animation is how much spatial and temporal variation there is in this relationship. And we can really rely on the CTM to help us look at how this relationship changes with time, and again, pair that up effectively with the satellite observations to relate AOD to PM 2.5. Different groups will talk about different approaches in this, so it is worth clarifying now. This is the approach that our group takes. And in doing this, we produce what we call our geophysical estimates. We take those AODs and relate them to PM 2.5. And this provides a data set which has relatively good representation, especially at global scales, providing spatial and temporal representation of PM 2.5. Now, of course, we can go one step further by interpreting the differences between ground-based observations and those geophysical estimates to further enhance and further refine these estimates. To give you an example of how this looks, I've plotted here, this is just a simple plot showing the difference between those geophysical estimates, basically have no ground-based information in them, comparing, simply subtracting those from the ground-based monitors themselves. If you spend some time looking at this, you begin to see different features start to pop out. You can see regions with large-scale overestimates or underestimates or high variability. And so what effectively we do is we interpret these differences, these biases essentially, within a statistical framework and associate them with different parameters that we know affect the quality of those geophysical estimates. In doing that, then we can go ahead and further refine the surface of PM 2.5 and even better represent that PM 2.5 around the world. And a real strength of this particular approach is that it provides a consistent long-term representation of global PM 2.5. And that further allows
Okay, it appears as though we've lost Aaron temporarily, but I'm sure he will join shortly. I think while he does, I'll just field a question that came through the Q&A, which I suppose is a general question to any users of satellite observation. Someone was asking about tropotropospheric NO2 data that they're making use of, and were asking why they're getting negative values. And so negative values can occur over background regions or rural regions that might result from an issue with the estimate of the stratospheric column. So the stratospheric column might be large in that estimate. And so when you remove it from the total column, it can lead to negative values. But I would say for any kind of use of these satellite data products, it's always good to get in contact with the data developers just to confirm that you're using the data correctly and that it makes sense that there are negative values. Or you might actually be helping them out by pointing out an issue with the data product that you're using. I see that Aaron hasn't joined, so I think what we'll do is we'll move on to Yuming Gao from Monash University, and Aaron can come back and do part 2 of his talk when he's been able to rejoin.
Hi, everyone. Firstly, I would like to thank you, HEI, for the invitation. It is a great time to discuss and share some of my thoughts about using satellite data for air quality exposure assessment and epidemiology. Thank you for the opportunity. This is outline for this presentation. I want to talk about why we perform air pollution exposure assessment and what is the measurement error and the challenges. And how about using machine learning and the role of satellite data for the air pollution exposure assessment? And particularly, I will talk about the wildfire smoke exposure assessment and give some opportunities, discussion for this area. Is why perform air pollution exposure assessment? Actually, if we want to assess the impact of air pollution on human health, we need to get the exposure data to get the effect estimate for the relationship between air pollution and human health. And also, if we want to calculate the attributable disease burden from air pollution, we also need the exposure level of air pollution. So this is why we need to perform air pollution exposure assessment and to get air pollution data. Actually, currently, I think most of you have known that around the world there are limited exposure data for both space scale and time scale. For example, at the global level, some countries have many monitoring stations, but some countries or some regions still have limited air quality monitor stations. So if we want to measure the relationship between air pollution and human health, we need to get the data at that area without air pollution data. And also, if we even for some cities, they have many air pollution data or air quality monitoring stations. But if we look at a specific area like a rural area, a regional area, there are no monitoring stations. That is still require the air pollution exposure assessment to get the air pollution data. So what variables are involved in the air pollution exposure assessment? Generally, in the last 20 years, I think many studies have tried to use satellite data to get the air quality data. For example, using AOD to estimate PM5 and using some the ozone column to calculate the AO2 exposure. And also some other variables are also involved, like land use information, for example, the greenish road density, urban cover, and also importantly, weather conditions are also considered as important predictors for the air pollution data. For example, temperature, humidity, rainfall, and wind speed. All of them are very important for the prediction of air pollution data. And also because air pollution have a high spatial temporal correlation, and there is a seasonal trend or time trend. So we can model the air pollution data using the spatial temporal model and put the spatial temporal variables into the model to predict the air pollution data. And also there are some other important predictors like the wildfire data, population density data. So if we have all of this data, we can put all of them together into a model and to predict air pollution data to get the precise or accurate assessment. So here I will talk about my thought about the measurement error in the exposure assessment for air pollution. So here's an example about estimating the spatial temporal distribution of PM1 concentrations in China. This is using satellite data, meteorological data, and using information data. We blend them together to predict the PM1, daily PM1 concentrations. From this figure, we can see the left is actually the relationship between estimated daily PM1 and the observed daily average PM1. So we can say the relationship between the estimated and observed R square is 60%. The RMSE it's about 22 or 23. So that is that's still far away to R square 100%. If there is there is a large gap between the estimated and the measured. That means there is some measurement error, or we can say random error or fixed error. For the middle one, that is the monthly average, and for the right one, that is the annual average. We can see for all of them, there's still not capture the gap between the estimated concentration and the observed concentration. So if there is a measurement error, what is this error? What is the impact of this measurement error for the relationship between air pollution and human health? Here is a study. I simulated some scenarios for the relationship between exposure and the response. For the response Y, I simulated a Poisson distribution, and for the Y, we can assume it as air pollution PM5. For the top left, that is there is no measurement error for the X and Y. We can say for the green for the blue color line, that is the relationship between the exposure with measurement error and Y and the response. For the red one, that is the observed, the true X and the Y, a relationship between true X and Y. We can say for the top left, if there is no measurement error for both X and Y, there is no bias. That means the relationship between X and Y is true. But for the top right, if the X has a small random measurement error, the relationship between X and Y are slightly biased. That means that is slightly lower than the true relationship. But if for the bottom left one, that is the X with a large random measurement error. So we can see for the relationship between X and Y, it is that is lower, largely lower than the true relationship. But for the if the X has a fixed measurement error, there is no impact for the relationship between X and Y for the true relationship. So yeah, that means the more accurate exposure assessment, the more accurate effect estimate, and the more accurate estimation of disease burden. That is, some conclusion. And also there are some challenges for this field. The first challenge that is, there are many missing values in satellite data. We can say for the top left, that is original data, considering the varying pixel sizes. For the top right, that is high resolution graded data with no filling of the empty grids. For the bottom left, that is the high resolution graded data with spatial filling at the edge of the swath. We can say that for all of them, there are still some missing values in the satellite data. So if we want to put this data into prediction of evolution data, so we need to think about if this missing data can introduce some bias or some measurement error. So this is a challenge area, and here, this is an example for the solutions to fill in the missing values of satellite data. So we propose some method. For example, we use machine learning method to fill the missed values of satellite data, or we use kriging and inverse distance weighting and other method. So, and we compared which method is better. Generally, the machine learning method like random forest or extreme gradient boost have a better performance to fill the missing values of satellite data. But even they are better, but there are still some challenge because we can't make sure the field missing values can 100% capture the missing value to that is 100% correct, or this can be used to predict the evolution of PM5. And this time we talking about which machine learning method have been used in this area. So which models are usually used in this field for the evolution exposure assessment? At the very beginning, the linear regression is used to do the prediction, and then step by step it is expanded to generalized linear regression, generalized additive regression, GLM or GEM, and then expanded to mixed effect model and basis spatial temporal model, and also geospatial model like kriging, inverse distance weighting, and other geospatial model. And also, chemical transport model are widely used in this field to predict the evolution. And most recently, because machine learning and deep learning developed very quickly, and it has been introduced to this area to improve the evolution exposure assessment. And also, there is another, we call it land use regression model, but this one is just we put the land use information as predictors into linear regression or generalized linear regression or generalized additive regression or mixed effect model. Then we call it land use regression, but that is not a special regression. That is just linear regression or other regression models, but just to put land use information into the model. Regarding the machine learning model in the air pollution exposure assessment, there are still some challenges. For example, how to choose the machine learning models and which one is best, and how to apply machine learning in environmental exposure assessment easily. And do example machine learning models perform better than single machine learning model? Generally, in the last round talk by Dr. Chen Di and another person, they have given some examples. For example, they have compared the example machine learning and the single machine learning, like random forest or extreme gradient boost. Generally, the example machine learning has a high performance than the single machine learning. And here I want to introduce another one, which is just developed by our group. We call it deep example machine learning model. And this machine learning model as three-step or three-state machine learning. The first state, we use several single machine learning methods to predict the air pollution data using many predictors. And then for the second state, we use the predicted air pollution data from the single machine learning model to predict another state air pollution data. For example, for the second state, we can use random forest, XGBoost, or GLM, or support vector model to predict, the air pollution data again. And then if we get several predictions, and then we can use the weighted. We can weight these predictions by the negative least square to get the weighted predictions. So this one is a general structure of this deep ensemble machine learning. So what is the performance for this model comparing with the single machine learning or super learning? So we can say if we use the data from Italy from 2015 to 2019. This is daily data from about 135 monitor stations for PM5, and we got predictors for example, weather conditions and AOD data, and also land use data, and then we put them together to predict PM5 using different machine learning model. So, for example, if we compare the performance of this machine learning model in 2015, the R square from GBM, that is 0.69, or SVM, that is 0.9, or random forest, that is 0.85, or XGBoost, that's 0.5, 0.81. For the super learning, that is 0.85. For the deeper ensemble machine learning, 0.89. That is, the R square is higher than any of them, and also the RMSE is lower than the single one. And these results are similar for all the other years. So we can say that means deeper ensemble machine learning can give high performance for the prediction with a high R square and a lower RMSE. That means they can give a more accurate prediction. And for the deep ensemble machine learning, there are some advantages. For example, it has high prediction performance, and it avoids overfitting through cross-validation analysis, and it can set the optimal non-negative weight for each base model, single model or meta model, and it can minimize extent to the empirical experience in selected models. So we can set that automatically in the deeper package. We have developed the deeper package, the R package. It can be downloaded from GitHub, and this model can assess and compare the model's results directly from this deep ensemble machine learning package. And there are also some disadvantage. For example, we should be cautious to select the features, and how to select them. We still need to take care and to compare which features are best. And also, this model is very sensitive to the missing values, as I said, because of the satellite data has some missing values. So if these missing values can affect the model performance, that is still needed to be solved. And also, for this model, it needed more time to run a big data. For example, for the Italy data, maybe we need to run 2 hours using the deep ensemble machine learning. But for the random forest, it's just using maybe 1 hour or 50 minutes. That can be used to predict this whole national data. Here is the role of satellite data, and also using the same Italy data, we compared if we put AOD into the model to predict the daily PM5, and the results from the model which do not use AOD data. So we can say for the left figure, that is the model performance. For the model without using AOD data, and for the right, that is the model performance for the model without AOD data. We can say generally these two models have very similar performance. That means sometimes even we don't use AOD data for the daily PM5 prediction, the model is still quite well. So we should think about sometimes we might not need AOD data into the to predict the daily PM5 data, because sometimes there are many missing values, and also the AOD data is not the daily average. It's just to capture 1 hour or 2 hour data from the location. So here is some thought. In the following some scenarios we might not need satellite data. For example, if we have enough observed air pollution data and predictors, and these predictors are highly correlated with satellite data, and this study will restricted to a specific region. For example, we have national data in Italy, and we want to predict the data in Italy, and we have enough predictors and many observed air pollution data. So that means we can use we don't need to use AOD data. We don't need to use satellite data, and also we should not predict air pollution data in the locations which are far away from the training region. For example, if we have Italy data, but we want to predict air pollution in Spain, in China, that means that's can't be that can't be used. This model can't be applied. So that means we still need to use AOD data, and we can't predict air pollution data in the period that is outside the training period. For example, we have data from 2016 and 2020, but we can't use the model to predict the data, to predict air pollution in 2000 to 2005, because we don't have the data to calibrate the relationship between the predictors and the observed data in that period. So correspondingly, in some scenarios, we still need satellite data. For example, we have limited observed air pollution data and predictors in a specific region. The AOD data is still helpful to improve the prediction. And the predictor, and we want to predict air pollution in the locations which are far away from the training region. For example, if we want to predict the air pollution data in China, but we still need, and we only have data in Italy. That means sometimes we still need the AOD data, because AOD data is highly correlated with the PM5 with PM5 data. And then if we don't have the relationship between AOD and the PM5, we just have the weather data. The weather data, the relationship between weather data and PM5 in Italy, that can't be applied to China. And also, we want to predict air pollution in the period outside of the training period. We still need AOD data, because there is a high correlation between AOD and PM5. Here I want to talk about some example, some results for the wildfire smoke exposure assessment, because in recent years wildfire is more and more frequent, and it is lasting longer and longer. And also sometimes the wildfire smoke is spreading far away from the wildfire place to another place. For example, the 2019 and 2020 wildfire in Australia. The wildfire smoke had spread from Australia to South America. That means the wildfire smoke is a very serious health impact. That is affecting the people far away from Australia. So we need to find a way to calculate wildfire smoke concentration, and to assess its impact on human health. Generally, there are some methods or solutions to calculate or to predict the daily concentrations of wildfire PM5, wildfire smoke, wildfire PM5, or bushfire PM5. So we need to have the data. For example, we should have the ground-based PM5, satellite data, meteorological data, then use information data or other data. So we can use them, combine it together to develop a machine learning or maybe a general model. And then we can predict the total PM5 data. And then we also should have the chemical transport model to get the concentration of total PM5 and the concentration of wildfire smoke data. And then we can get the percentage of the percentage between wildfire smoke and the total air pollution data. And then we can use this percentage, multiply the total concentration from the output for machine learning, and then we can calculate the wildfire smoke data or specifically for wildfire PM5 data. Here is an example. We get some global data set. We have the monitored data from open source data, and then we use this data to calculate the total. We use this data combined with this machine learning and chemical transport model to predict total PM5 and wildfire PM5. And here is the model performance for the machine learning, and we get R square is 70%, and the IMSE is 25, about 26 microgram. Okay, and also for the right figure, that is the calculated the maximum level of daily wildfire relative PM5, and then we can apply this estimated data with the global health data. So here is we collected a multi-country, multi-city data for mortality. This is MCC database, which is organized by Professor Antonio Gasparelli and me and other colleagues across 43 countries. And then we matched this daily mortality data with the estimated wildfire PM5 data, and then we calculated and estimated the relationship between the daily wildfire PM5 and the total mortality and the cardiovascular mortality and the respiratory mortality. So we can see for all of these mortality types, there is a relationship between wildfire smoke and this mortality. And also, we can see there is acute effect, that is, the wildfire smoke can immediately increase the mortality risk at the current day. Let me see if there is a wildfire smoke today, the mortality risk will increase today, and this effect will last about 2 to 3 days. And here is, some challenges. There are still some challenges in estimating the wildfire smoke. For example, currently many studies just simply use the total concentrations of air pollutants during the fire period as the wildfire-related concentrations. Generally, that is not very precise because, if we just use the total concentration of the air pollutants, so we can't remove the background air pollution data. And also, currently, the spatial resolution is still very low, because the output of the chemical transport model is not with high resolution. That means we still need to think a way how to improve the resolution, how to make the resolution higher. And also, it is hard to directly validate the wildfire smoke concentration with the measured air pollution data, because there are very few monitors in the rural area or in the rural area. But sometimes the wildfire happen in the rural area, in the forest. If we don't have the monitors in the wildfire places, we can't check what is the real concentration for the wildfire smoke. We still need maybe we still need to put more monitoring stations, across different area. And also, most monitoring stations are located in the urban area. For this urban areas data, it's already included the urban background air pollution data and the wildfire smoke data. So how to separate them? We need to, to find a way. Of course, there are many opportunities in this area. For example, there are many available big data. For example, we have many observed data, including the low-cost census data. Currently, there are many low-cost sensors have been developed and used in different countries. Maybe in the future we can combine them, or maybe currently many studies or many groups have already applied this data to do prediction. But the low-cost sensors sometimes we still need to validate them or calibrate them. Sometimes they are not very accurate. And also the remote sensing data is more and more satellite launched, and the remote sensing data are available, and several of them have been open to use. So we can download them and combine them to predict. And also the weather data is available, and many groups have already performed very good study to predict the weather data across the world. And that because the weather data have a very high spatial correlation and the temporal correlation. Generally, their prediction are much more their prediction have higher performance than the air pollution prediction, because the weather data, as I said, have a very high spatial temporal correlation. And all this data make it possible for the performance for the accurate prediction. And also the machine learning, deep learning technologies are developed very quickly, and it provides a better prediction performance than the traditional models. And then we can use them to do some work. Because the machine learning and deep learning technology need a high performance computer, and currently there are many cloud analysis platform or high performance computer platform can be used and are available to perform the big data analysis. So we can think about how to combine them together to improve the accuracy for assessment. Okay, thank you very much.
Thank you, Yuming. That was fabulous. I think in the interest of time, there were a couple of clarifying questions on the Q&A, but I think we will wait until the end of the talk. And if that's okay, you might want to look at the questions and maybe respond, Yuming. Let's switch back to Aaron now, because we lost him in between. Aaron, do you want to continue with your presentation, and then we can come back? The rest of the speakers. Yeah, please.
All right, thank you. Thank you very much. Let me just share my screen here. All right, so I guess very, very quick recap. Most of it's been covered. I believe I was about here when I cut out. So a real strength of the approach that our group takes towards providing PM2.5 estimates from satellite is it provides a consistent long-term representation of PM2.5 with global coverage. And this allows you to do some really interesting things. You look around the world and assess global air pollution really all over the world. I'm not exactly sure where I cut out, but so briefly here, this plot is showing basically linear trends of PM2.5 from 1998 to 2018. And essentially in this plot, the intensity of color is showing the significance of those linear trends. And as we look at this, a couple really interesting features pop out, particularly over North America and Europe, where we can see these nice downward trends over this entire time series that agree very nicely with cross-validated PM2.5 observations. Now, of course, as we discussed a little bit in the last workshop, metrics are really important in trying to assess the quality of estimates, but also in terms of how you evaluate what's going on. And here is where a linear trend often doesn't do justice, especially over India and China. And so over India and China, if we look at the linear trends, what we see is this large increase in concentration, very significant increase in concentration through to about 2010, 2012. And what begins to happen, especially over China, is a number of government initiatives begin to kick in, specifically designed to address PM2.5 concentrations in that country. And we can see just how huge a success those have been. We see that complete reversal of trends over this area. So here we see, of course, switching from increases of about a microgram per cubic meter per year up to about that time period to this dramatic increase, the largest decrease anywhere on the planet over this time period of between 3 and 4 micrograms per cubic meter per year. Over India, we see a similar increase leading up to about 2010, 2012, but more of a stabilizing PM2.5 at that point. An alternative way to interpret these results is also using population-weighted PM2.5 distributions. And these provide direct insight into how changing PM2.5 concentrations impact local populations. For example, here, if we look over at the start of our time series in 1998, you can see population-weighted mean concentrations over North America and Europe at about 15 micrograms per cubic meter. China and India being a fair bit higher at around 50 micrograms per cubic meter. And if you remember that trend plot I showed on the previous slide, you begin to see North America and Europe start to diverge quite dramatically from over China and India, with concentrations lowering over the first regions and over China and India really increasing, those population concentrations getting higher. Now, as government initiatives start to kick in, we begin to see more features start to change here, with Chinese concentrations decreasing down, still very, very high, obviously, but certainly improving compared to where they were earlier in this time series. Down below, I've shown here, this is just the same plot, except looking at the linear trend, a population with linear trends over the same time series. Now, in addition to these long-term changes, seasonal patterns in PM2.5 can also be quite significant. And here's where data such as this can also be quite insightful. So here it follows similar methodologies to what I was discussing a little while ago at this point, but taking those methodologies and further refine them down to allow monthly PM2.5 estimates around the world. What I really want to highlight here is how much of an impact different seasons can have in terms of exposures. So here over North America and Europe and parts of Asia, I've shown mean PM2.5 concentrations for January as well as July. And I've capped these different regions at different levels just to correspond with the sort of PM2.5 pollution we see in these regions, with North America capped at 20 micrograms per cubic meter, Europe at 30, and this part of Asia is capped at 120. In all cases, they saturate sometimes, but really what I want to highlight here is how dramatic that seasonal variation can be. If we look over North America, for example, you can see the San Joaquin Valley really being a hotspot, quite high pollution, at least from a North American standpoint. And if we contrast that in the summer, we can see other features start to pop up. We see wildfire burning, of course, parts of Canada, as well as parts of California, as well as other sources of organics further in the south. Over Europe and Asia, we really see much higher concentrations typically in the winter compared to the summer. And this affects the population as a whole. If we look down here, this is a population-weighted distribution of PM2.5 concentration. Although over North America, the distribution does change within the continent, the overall population distribution really isn't changed that dramatically from January to July, especially when compared to the amount of change we see over Asia, where we can see the entire population really shifts from we'll say relatively low concentrations to relatively high concentrations between July and January. Now, in order to address these enhanced PM2.5 concentrations, be they seasonal or annual, policymakers really require insight into what's driving PM2.5 levels. And here's where some recent work undertaken within our group by Erin McDuffie has really sought to help policymakers address to answer these questions. Where is it coming from? Her specific work was working on updating the emission inventories used by GeoChem, specifically updating the inventories over Africa and India, extending their time series, but perhaps most interesting from a policy standpoint, she also included the ability to retain fuel type information. And what this allowed her to do was take this information, run it through GeoChem, through a CTM, combine it with the satellite observations to produce an overall burden of an estimate of the burden associated with PM2.5, but also break down that burden by different fuel type contributions, such as the contribution from coal here shown in black, or from residential burning shown here in this light blue. And these insights are perhaps most relevant when taken on a national scale, where it can motivate government initiatives to reduce PM2.5 concentrations. For example, the burning of coal in China is estimated to cause about a quarter of the PM2.5 related deaths there. Or the burning of biofuels associated with around a third of such deaths over parts of Southern Asia. And this is in contrast compared to over the United States, where oil and gas burning tends to dominate that overall PM2.5 related health burden. And ground-based observations can again be used here to enhance our understanding of PM2.5 sources via estimates of PM2.5 composition. Here we use a similar approach as we did for PM2.5 total mass, taking advantage of the unique strengths of satellites and ground-based observations and chemical transport modeling. Specifically, we take those hybrid estimates of PM2.5, which I talked about again, it's a little while ago at this point, but take to those initial hybrid estimates of total composition and apply to them the relative contribution, according to GSChem, of individual components to produce an initial estimate of, say, sulfate or nitrate or organics. And then we go ahead and further refine that by investigating the difference between these initial estimates and observations on the ground. And in this case, it's a North American-based data set, but really this approach can be taken anywhere with a reasonable network of ground-based observations of composition. And the results are really quite solid, as you can see here in these comparisons with cross-validation shown in the gray here. And what this resulting data set allows is insight not only into the spatial and temporal variation of PM2.5, but also of its various constituents. And these constituents show unique and significant variation in both space and time, as shown on the right-hand side of the slide here. And so here, mean concentrations of sulfate and nitrate and organic matter shown for summertime over North America, as well as for wintertime. And what you can see is really summertime highs, at least historically, over the long term, have been driven by sulfate, more in the east, as well as over organics with a very different spatial pattern. Wintertime concentrations tend to be more driven by nitrate-based sources. We can also view this in terms of a time series as we watch how these concentrations and the contributions of the different components have changed with time. And so here shown over for North America as a whole here, we have this is a time series of PM2.5 with the organic contribution shown in green, the red showing the sulfate contribution, the blue showing the nitrate. And you can see that overall decrease, we talked about the trends, but also on top of that, you can see some really interesting features beginning to pop out, such as you see the summertime sulfate concentrations occurring very, very regularly with each summertime, but also as they die out with time, as again, government initiatives kick into place, specifically designed to address sulfate concentrations over North America. You can also really see in here how different regions of North America, and this would go for many different parts of the world, of course, but different regions are affected by different sources of PM2.5. You can see here over the northwestern US, for example, organic matter plays a really strong role in the PM2.5 concentrations there. And this is different compared to the Midwest, which has large nitrate sources from industry or agriculture, as well as the southern US, where again, we see that historically that seasonal bump related to sulfate, but then dying out as government initiatives kick in specifically to address that. This also really highlights how relatively clean areas can be seasonally relatively polluted, as shown here in a plot with northern Canada, an area that's typically very, very low, very clean environment, except for seasonally with biomass burning seasons, the population there can be exposed to more typical North American conditions. Now, as has hopefully been demonstrated throughout this presentation, modeling plays an important role in taking advantage of satellites and ground-based observations. These simulations, however, can be computationally prohibitive, especially at high resolutions. In order to help address this challenge, Liam Bindel, another member of our group, has been developing high performance capabilities within the GSChem framework. And these capabilities allow GSChem to be run in a massively parallel environment. It allows efficient scaling over thousands of cores, including usage on the Amazon cloud, which could be quite useful for a number of users. and recently has allowed global simulations at resolutions as fine as 12 kilometers, which for geochem is quite an accomplishment. Perhaps more excitingly to a general user base is the ability to stretch and change the geochem grid, such as you see in this animation here, allowing a high resolution simulation in one region while maintaining global transport from other regions at a relatively coarse resolution. And this allows essentially to run a high resolution simulation with all the advantages of the CTM at relatively low computational cost in regions that are less relevant to a particular study. So you can see down here in the simulation over North America, part of California, where this California section is run at about 12 kilometers again, but the overall computational cost is similar to that of a simulation run at several 100-kilometer resolution. And while PM 2.5 is primarily my own focus and is the focus of this presentation, other health-relevant pollutions can also be directly viewed from space, such as NO2. As with PM 2.5, satellites provide insight into the total column, and surface concentrations can then be inferred by applying a CTM-based relationship. Unlike PM 2.5, however, spatial variation of NO2 occurs on scales that are the order of kilometers or finer, which historically has been prohibitive due to the relatively coarse resolution of CTMs. Recent instrumental and algorithmic developments, however, have begun to allow a more complete representation. And with respect to instrumentation, as was mentioned during the introduction remarks, Trabomi provides a fine-scale global representation with a resolution of on the order of kilometers and is adding to the growing geostationary complement provided by GEMS presently and soon to be launched over Tempo and Sentinel as well. But returning to PM 2.5, the complete lack of ground-based observations over many parts of the world present a significant barrier and likely limit the quality of satellite-derived estimates. The Surface Particulate Matter Network, or SPARTAN, is a global network of ground-based PM2.5 monitors specifically designed to add high-quality monitoring capabilities to regions. And our group is quite proud to be a part of this network. It really leverages off the locations of existing sun photometers. And in doing so, it provides insight not only into PM2.5 and its composition, but also direct measurements of the AOD to PM2.5 relationship that's so essential to taking advantage of satellite observations. Specifically, SPARTAN provides filter-based measurements in a fairly semi-autonomous fashion, so with very little operator requirements. It couples those with the nephelometer to provide high temporal resolution information, and again, combines that with a sun photometer-based measurement of AOD, again, for direct calibration to satellite sources, satellite retrievals of AOD. SPARTAN is proud to be part of providing support for the upcoming Maya missions, come up a few times, and really a great initiative for trying to, again, address that sparsity, that paucity of measurements in many parts of the world. So hopefully this has given you some idea of how satellite-derived products can take advantage of multiple data sources to provide high-quality estimates of air pollution that is both spatially and temporally complete, as well as how these data sources can be used to provide insight into not only PM2.5, but also the sectors and sources and components associated with these concentrations. Developments continue to occur within this data set, driven by the continued development of not only satellite instrumentation itself, which is of course key, but also developments for chemical transfer models and ground-based monitors with which they are essentially coupled. Thank you very much.
Thank you, Aaron. That was terrific. I think we will have to move on in the interest of time, not to take any clarifying questions, but we have several in the Q&A posted that you might want to take a look. We will transition now to the three global applications. With the first one from India. The presentation will be made by Sagnik Day using satellite PM2.5 for air quality management and health studies, lessons learned in India. Sagnik is Institute Chair Professor at the Center for Atmospheric Sciences at IIT Delhi. Sagnik.
Yeah, thanks, Kalpana. Hope I am audible and my slides are visible.
Yes.
Yeah, perfect. So good morning, good evening. I want to take this opportunity to thank Health Effects Institute for providing me this opportunity to talk about the exciting and positive development in India. So our Central Pollution Control Board, who is the regulatory agency, they have recently started exploring satellite data in air quality management. And the reason is that if you look at the distribution of ground networks in India, three things are notable. One is that if you look, we have around 800 manual monitors and 340 plus continuous monitors. Although this number looks reasonable, but if you look at their distribution, they're disproportionately distributed. All the monitors are concentrated in few urban areas. It means that we're not really monitoring any rural or any regional background. And also, if you try to calculate the mean distance to the nearest monitor for exposure modeling using just the ground-based monitors, the number is on an average 80 kilometers. So clearly, and then also the other important point is that if you look at this figure and the color, which indicates the year from which this monitoring started. So most of the monitoring sites in India became operational only after 2016 or 17. So we really do not have a very long-term data sets. And that's why CPCB started looking into the satellite data as a complementary tool. And I will just give in the next 5 minutes some examples how this data are used for air quality management as well as the health impact assessments. So we put together this database for the government. This is just an example of the climatology over 20 years, annual climatology, and then this is how the satellite data performance looks like. This is the daily scale. You can see that the R square is around 0.8, and the annual scale, the R square is around 0.97. The root mean square around 7. The most important thing is that now the Central Pollution Control Board has agreed to host this data and disseminate through their own data portal. So it means that, not just for the government use, but for any user can have a free access to the data. And if anyone wants to get access before this portal is made open, I will be very happy to share this. So one example is that because air quality is such a big issue in India, our government has announced this National Clean Air Program, and with the base year 2017. So what I'm showing here is how the number of days. So this color scale indicates how many days PM 2.5 level exceeded the daily national standard, which in India is 60 microgram per cubic meter. And if you see in the recent years, what happened is that there is a transition from red to blue. It means that the number of days pollution level exceeding the national standard has come down. And in fact, if you just recall what Aaron showed in stock over India, there is a kind of stabilization, which we are also getting from our data sets. So from 2000 onwards, there is a very sharp rise in pollution in India, but mostly from 2016-17, the trend become kind of stable. Then there are many other applications which we are working with the government. For example, this is where actually we have used this satellite data to define major airsheds in the country. And this is just an example for the regional airsheds during the winter months. And you can see that for each airshed, what is the typical seasonal concentrations. These points are actually the ground-based measurements. And then we are trying to understand how in these airsheds pollution varies at various temporal scale. Using this data, we are zooming into the city. For example, this is an example of Delhi where you can identify the hotspots, trying to understand what are the local sources. And because it's a satellite data, it also provides the information outside the city, so one can actually keep track what is happening locally versus regionally. The other very important applications that the government is doing using such kind of satellite data is to understand the environmental carrying capacity. As I mentioned that we do not have really any measurement outside the cities. This is one example in Delhi and surrounding areas. And this is actually annual concentration in 2021. And all these points which you are seeing, these are brick cleans. And you know that in India, brick cleans are major point sources. So basically, here the objective was to understand the regions where these brick cleans are located. what is the pollution level, how frequently the pollution level exceeded the national standard, and in which parts of this region, the brick lanes can be operated, given that this kind of variations in the air quality. Then the other very important application is to help the government in identifying the future ground-based monitoring locations, because obviously within limited resource, we cannot really expand randomly. So what we are doing is that we're looking into the satellite data over the last 20 years, and then we're working with the government with a set of criteria to understand that where we need actually ground-based monitor, depending on where the pollution level is high or increasing at a faster rate. But at the same time, I think this is a good opportunity that more and more such expansion happens, that in turn will help actually improving the satellite data products. Not just air quality management, but there are multiple health studies conducted already using this type of satellite data in India, using time series design or cross-sectional studies, or even retrospective cohorts, and many more actually are being planned. So finally, I want to demonstrate like where we are moving. So obviously, we are talking about satellite PM 2.5, but now there is an opportunity to integrate this satellite data with the ground-based measurements of ambient air quality, and also very limited indoor measurements, particularly taken during this multiple cohorts that either was conducted earlier or currently are ongoing. And then if you integrate all these informations along with the time activity profiles of the target populations, I feel that there is a strong opportunity that we can finally reconstruct personal PM 2.5 exposure for target populations. And this can be validated again, against some gold standard measurements conducted in these different cohorts. And eventually this will lead to generating long-term PM 2.5 exposure data for various target vulnerable populations. In India already, many of these cohorts either are ongoing or just ended with enormous potentials to further collaborate. And in fact, I'm looking forward to collaborate with Kalpana's group and any other group who are involved in this type of cohort studies in future to further take it next level. So just in my concluding remarks, I want to tell that, as I mentioned, the satellite data products are being now increasingly used in India. Particularly the heartening thing to see is that the government is kind of adopting this satellite-based data for air quality management. And obviously, health impact assessment will continue. There are new products which are in pipeline. For example, we are planning to come up with an hourly PM 2.5 product, PM 2.5 species product, as well as sectoral PM 2.5. But these are mostly using the methodology which Aaron and Young already explained earlier. And finally, also a synergy is being evolved to integrate ground-based reference grade satellite as well as low-cost sensors, so that to understand how we can improve further exposure modeling and then apply for health studies. So with that, I thank you for your attention.
Thank you, Sagnik. That's a fantastic illustration of actual application in a other difficult, situation with rather low density of monitor networks in many areas of India, and a regulatory authority having to, having accepted this as a way forward, and to host in the portal is indeed a major accomplishment. So thank you both for your presentation and for this important breakthrough with this application. I will move on now to a case study from Colombia that Laura Rodriguez will present, using satellite-based air quality global models to estimate surface PM 2.5 concentrations and avoidable mortality in Colombia. And Laura is an associate professor at the Department of Public Health School of Medicine at the UIS in Colombia. Laura, over to you.
Good morning, everyone. Please can you confirm you can hear me well and see my presentation?
Yeah, that's perfect.
Okay, thank you. So I want to thank the organizing committee for this great session and workshop at the Health Effects Institute. And for this specific part, I want to share with you our experience using satellite-based models to estimate particularly medical concentration and epidemiological mortality, and presenting on behalf of a team group in Colombia, South America, that is part of the GeoHealth Hub Colombia and part of the Air Quality Urban and Urban Environmental Health in 5 cities in Colombia project. So the first thing that I want to mention is that in Colombia, we have a national quality network that is coordinated, supervised by the Ministry of the Environment, and currently is composed by 24 surveillance systems. For the year 2019, we have 92 ground monitor stations for PM2.5. And as you can see in this map, we have concentrated location for those monitor stations, and parts of the country, especially the south and southeast of the country, is lacking of a monitor station, and is the place of the country where most of the biomass burning occurs. So basically we have the surveillance system concentration in large cities that we don't have enough information for small and medium-sized cities. The use of satellite-based data is an alternative tool to have estimation of PM2 concentrations at municipality level. As an example, for 2019, we had information only for 28 out of 1,100 municipalities in Colombia. So using this satellite-based tools are useful. So for this specific work, I need to compare 2 air quality global models that are available. We use estimation of PM2.5 surface concentrations for the atmospheric composition analysis group model that the Dr. Fondoncolor just presented moments ago. We call ACAG model. For the Copernicus Atmospheric Monitoring Service, the CAMSRA model. For both models, you use the estimation of concentration at 0.1 degree resolution, and with the average concentration per year for each municipality during the time period of 2014 to 2019. As I mentioned, we had information of ground monitor station available for 20 municipalities for 2019. So we made a comparison of the estimation of the satellite-based models with the monitoring stations. And choosing one of those models, finally, we use the data for annual mortality and the estimations of total naturally specific cause of mortality that were released in 2020 from meta-analysis to calculate the number of avoidable deaths that are related to the excess of exposure to PM2.5 concentrations above our current national standard, that is 25 micrograms per cubic meter, and the projected standard for 2030, that is 15 micrograms per cubic meter, that it corresponds to the WHO interim target number 3, according to the updated guidelines in 2021. So these maps are showing the results of the estimation of surface concentrations for both models in Colombia during 2019. And as you can see, both models show high concentration in the north part of the country, the northeast, but the CAMSRA model show a higher concentration around the Bogota, the capital city, and the surrounding municipalities. And in contrast, the ACAG model show higher concentration at the southeast municipalities of Colombia, which are the zones where most of the burning biomass occurs, that is the Amazon area of the country. Overall, the CAMSRA estimations, the CAMSRA model estimation are a little bit higher for most municipalities compared to the ACAG model. And when we compare those estimations from the cities that have available information, the 28 cities that have available information for 2019, we found the ACAG model to have a lower bias that was 1.7 micrograms per cubic meter, and it was lower from the ones obtained for the Kamstra model that was 4.7 microgram per cubic meter. These are graphs that are showing the dispersion of the difference between the estimation and the ground concentration, and the red lines are showing the mean bias and the 95% confidence interval for the Bland and Allman limits of agreement. So based on this comparison with ground monitoring station, we decided to use the ACAG model to estimate the number of avoidable deaths using both standards. So these maps are showing the numbers of deaths that could be avoided during those years, 2014 to 2019, using as standard 25, that's our current national standard, and it resulted in 142 avoidable deaths. But when you use the standard of 15 micrograms per cubic meter, it results in an estimation of over 34,000 avoidable deaths. The comparison between those models, between those standards, are a key important message, showing the impact of having decreased standard regulation for countries such as Colombia in terms of the amount of death that can be avoided. So in conclusion, satellite-based air quality models are useful tools for estimating the surface concentration for PM2.5 at municipality scale in Colombia, even though the models were developed at a global scale, and that we know the levels of uncertainty for the ACAG model are higher for this part of the world in South America, where less ground monitoring stations were available for fitting the model. But besides these considerations, the model seems to have a good estimation of the concentration over the country and over the different areas of the country. And for sure, we'll need more work to be calibrated with local data for better accuracy. In terms of the avoidable mortality, we think that these results comparing the current and the projected national standard are an important input for that might be considered by decision makers to decrease or review the current national standards in line with the WHO guidelines that are now in place. So thank you very much, and I'll be open for your questions.
Excellent, thank you, Laura. And then we move on to South Africa, where Rebecca Garland, who is an associate professor at University of Pretoria, is working hard to convince local authorities and decision makers there to take up satellite observations.
Great, thank you for the introduction, Eloise. Can you hear and see my video okay?
Yep, perfect.
Great. All right, good morning, good afternoon, good evening. Thanks for having me, and I'll finish off this session before the questions with a little bit more of a forward view. And so, you know, I work on air quality issues in South Africa at the University of Pretoria, and while Earth observation data have been used in many fields in South Africa, a lot of times it's terrestrial work. There isn't a lot of advanced use of air quality satellite measurements for air quality purposes in South Africa. And then just from, you know, from speaking with networks and literature, that's true across a lot of Africa. So there are, of course, studies, but there's still really a lot of untapped potential. And so using Southern Africa as an example, that's what I'd like to just talk on today very quickly, are just some views on the untapped potential of satellite measurements for understanding air quality in this region. And so, like I said, a little bit more of a forward view. So I'm speaking of Southern Africa, not just South Africa, because, we're very connected in our atmospheric composition. That's two main things. On the left-hand side here, we have the large-scale biomass burning that happens in the Southern Hemisphere winter going into the spring. What you see on that figure, it's from the Safari 2000 campaign, where you have this river of smoke coming off of Durban, which is the Indian Ocean side of South Africa. And then we also have the transport patterns that can set up this really strong anticyclonic system that can just recirculate the pollution around the whole Southern Africa. You can see it also has the exit pathway shown here over Durban. And so, speaking of, of regional pollution, one of the main one is the biomass burning. And so just to show the large scale of this, I'm just going to show one tropomi from our winter rather, and then one during our biomass burning period. So this is tropomi, satellite measurements of tropospheric column NO2 from June 2021. So this is the monthly average. And up in the north, you can see there is NO2 coming from this most likely biomass burning this time of year. In South Africa, you can see our cities and our industry. But if we then look going towards when our biomass burning is much larger, all of the orange, I hope you can see it okay on your computer, but really you get a lot more dots of high levels of tropospheric column NO2 in Southern Africa. And really the whole area just gets a lot oranger during this period. So you can see the scale of the regional pollution. And this really makes a very interesting area to study. We have the regional characteristics, but there's also very strong spatial and temporal diversity of sources. We have natural sources, one of the large ones here, the biomass burning, but also very strong anthropogenic emissions. You could see them in South Africa towards the bottom with our cities and also some industry. But of course, there are other large cities in Southern Africa. And we are a data scarce region, and these regions have been noted in many of the talks today of a place where satellite information, of course, has a very important role. So just in general, Southern Africa is a very interesting and complex place with many different unanswered questions. And so the question that I come to in this is, what can we do or improve with the knowledge, the questions that we have? How can we start to answer them with satellite measurements that are available? Because many times when we're doing air quality management work in South Africa, we know we don't have perfect information, but can we still take a step forward? Can we get a little bit better? And I think satellite measurements really, that is an untapped potential to start to better understand the atmospheric composition and air quality. And when I think about this question, I just wanted to provide, some views on this. I think along the impact pathway, where you have the emissions of pollutants that are transported and transformed as they move about, with the resultant ambient concentrations that a receptor, people, plants and such can be exposed to and then impact. I think there's lots of areas for satellite measurements to play a role. And some of this is work that is just starting, so we don't have results yet, but this is also trying to think more broadly than just what my small group does. So one area that we do a lot of work in is emissions, and open data is a struggle for us. And very often, I think when we think about satellites, and even when we talk about open data, we think about ambient concentrations, but there's also a lot of information and data that needs to go into emission inventory. And this large uncertainty comes both in modeling, so running chemical transport model and the emission inventories that go in. That's particularly very often a spatial resolution issue, as well as the uncertainties in the input. And then also from a management, industrial emissions are very easy to estimate sometimes, and so those will be managed more than more community-based ones that can be harder. So the input data also have very large assumptions. And so, of course, satellite measurements can help to constrain these emissions. At least that's another point that we can look at to compare to, which will be very important. As I noted, we also have a regional pollution issue. Also, so this is now kind of getting to the transport and transformation, and the satellite, we could see even just in that simple qualitative analysis of that, picture from the tropomi measurements, we could see the regional pollution. Also, I would argue it'll give us a broader view on atmospheric composition. Currently, many ground-based measurements are for particulate matter, and of course, as an atmospheric scientist, particulate matter are very important, but they're not the only pollutant. We also do need to be concerned of the trace gases as well. And so we might be able to get a broader view with satellite measurements that incorporate also trace gases, where many of our ground-based are focused only on PM. And then, of course, we've seen quite a lot the importance of the consistent data, and we did see some really interesting trend work earlier as well. And I think, particularly for data scarce regions, this can be very important. It's very important for atmospheric composition, but also for impacts, where many times we have measurement campaigns that are very short-lived. And so, can we put that within the context of a larger trend? And also for policy analysis as well. And we've done that recently for South Africa using machine learning with collaborators at Emory University. But just to finish off, I just made a quick summarizing thoughts from some of these views that, satellite measurements, I do think have an untapped potential, but of course, multiple data streams are needed. I'm definitely not saying that ground-based measurements are not necessary. So other data streams are still needed, and the diversity of the sources and species that I showed, that's not unique to Southern Africa, just to show an example, but I think across all of Africa, there's this really interesting diversity. Open and consistent data have roles in research. We've talked a lot about that today. Policy as well, but also I think in environmental justice, in community and citizen science, and seeing, the impact, seeing the pollution from space, and being able to track some of the larger emitters. Of course, in Africa, technical and capacity barriers do exist, as in many places. From the technical aspects, this includes just how does one access, download, and analyze such large data sets. We don't always have high performance computing, or even, access to the cloud. Also with that, from a scientific point of view, if you do use data that are more analyzed, how do you keep track of what version you're using if you don't know? Also, that'll be there when the versions are updated as well. And just one last thing to note is that these data are available, but I think there's always the worry that it can lead to helicopter science, where researchers not in the local research, helicopter and do work without working with local researchers, and then leave. And that really, of course, I think has a large negative impact on the impact of the science. And I was asked to give one example, and I'll just note that here, and I also did send on the link, that this was an article written about the Safari 2000 campaign, the Anagon and Swap, but it's a good example, I think, of really moving towards more equitable and really true collaborations. They call them transformational and a mutually beneficial process. It's viewed through the eyes of science diplomacy, but really also has an links up to helicopter science. And just to note that the views I've shown quickly here were recently honed at a Lawrence Center workshop that we had. And so I want to acknowledge all the participants and organizers in that. And thank you again to the organizers of this for inviting me today. Thank you.
Perfect. Thank you, Rebecca. That's a very nice take on a difficult region. That brings us to the end of the presentations. So I just wanted to sort of sum it up a little bit. And of course, there will be some closing remarks at the end, but I think it was fantastic to have colleagues from all across the world share their experiences from real life application of satellite derived air quality data in India, Colombia, and South Africa, spanning 3 very diverse geographies, sources, and population densities. And both Yuming and Aaron talked about the potential, and as Rebecca mentioned, the untapped potential of such methods to fill regional or country level needs for air quality management. And also about the challenges related to the uncertainties in the exposure estimates, and those related to extracting and using the data for routine exposure surveillance, as well as for specialized health effects research. So we've come up with a few questions for the panelists, and both Eloise and I will alternate with asking these questions if it's okay to do so. And we have the first question for Yuming, if you could comment on. This is concerning the role of uncertainty and perhaps also measurement error in satellite-based exposure estimates for health burden calculations. Many, I'm sure you're flooded with requests from epidemiologists for you to give an answer on, can I use the satellite data for this particular study that we are doing? And so what would be your advice to health effects researchers, especially those working on building quantitative exposure response relationships in regions where there is, especially limited ground monitoring networks and emissions inventories are incomplete? Are we there yet to be able to give them a product that is readily usable in their particular study? What would be your general take on it?
Thanks, Kalpana, for the question. This is very interesting and important in this area. Can you hear me?
Yes,
You
we
might
can
need to
hear
speak
you.
up a little bit. Yeah.
Okay.
If all the other speakers want to join, so we see you all for the Q&A, that would be great.
Okay. Yes. Yes, there are many uncertainties and challenges in this area, but applying satellite data to predict air pollution, it is still highly reasonable and plausible, because if we don't use this data to do air pollution prediction, we can't do the health risk assessment and can't do the disease burden calculation. Even there are some uncertainty, but we still can give some information in this area. And generally, if there is some measurement error or the bias for the relationship between the estimated air pollution and human health, generally these effect estimates are assessed lower than the true relationship. That means the information are still there. If we can get there is a relationship, that means there is really has a relationship, but this relationship might be generally lower than the true relationship. So yeah, but we need to try our best to improve the exposure assessment to make it as accurate as we can. For example, we need to get more precise satellite data, or to remove the missing value, to find a way to interpolate the missing value from the AOD data. And also we should combine the other predictors like the weather data, because weather conditions, the weather data are highly spatial temporal correlated, and also they are correlated with AOD data. If there are not enough AOD data, we should use the weather data to replace the AOD data. So this is some experience I'm happy to share with you. Thank you.
Yeah, thank you. Eloise, do you want to go on with the next question?
Yeah, this is a question for Sagnik. It's related to convincing regulatory authorities and decision makers to get on side with the information that can be provided by satellite observation. So if you can just give your insight on what it took to convince regulatory authorities in India to take information up about air quality from satellites, including hosting the satellite-derived estimates of PM 2.5 on their portal. And also some, if you can provide us with some information about how far you are in being able to create a workforce that can then generate and use this data routinely.
Yeah, so first, why the regulatory agencies are now interested in utilizing satellite data. As I explained that we really do not have the adequate resource, frankly saying, for expanding the reference grid monitoring network that's required as per our own guidelines. In fact, we need at least 4,000 reference grid monitors based on the population distribution and all. And there are many instances, for example, where actually there are no data available. There are many public court cases regarding in the poor air quality. People are suffering and then filing petitions in the court saying that air quality is bad, do something. So at one hand, there are public pressures, and based on those things now, lot of actions, or rather I would say a lot of regulatory decisions have been taken more based on hunch rather than any data. And by hunch I mean either you just get a sense about the local emission profiles and think that okay, yeah, really these are contributing and all, but as I explained, like there is no sense of what is the regional air quality, how things are changing. Number two is that a lot of the attention till I would say 2016-17 was on the major urban areas. And then people realize that you cannot just do something within these cities and expect the city to be clean, because there are plenty of studies which showed that this entire Indo-Gangetic plain in the northern India has very high level of pollutions. And it's not just the urban sources. In fact, household emissions, still till today, household emissions is the single largest contributor to ambient PM 2.5 in India. And it shows that we need to really start measuring air quality in the rural areas too. Emissions are very different. So this urban rural gradient, which you typically see in US or Europe, it does not really exist in the northern Indian region. Any rural place you go, there is a huge amount of pollution. So all these things kind of, I would say, propelled the regulatory agency to start exploring the air quality data. And that's why they wanted to standardize the algorithm, do due diligence in terms of, evaluating the data product based on whatever limited data is available. And as I said, also use the satellite data as a basis to prioritize where in future you need to really expand your monitoring, given the fact that you have limited resource and you can only expand to certain limit. So all these things actually kind of contributed this effort. And right now we are maintaining the database at our local server, and to disseminate the data freely to everyone. CPCB has agreed to host the data. In terms of workforce, you asked, like typically we have a team who is maintaining, doing the daily processing and all. I'm trying to organize several, I already organized several training sessions for Central Pollution Control Board and various state boards, so that the regulatory agencies themselves can start exploring the data. It's not just we are producing and we are giving them the numbers and they're just looking at it.
That's really great. Thanks, Sagnik. And then over to you, Kalpana, with the next question.
Yeah, I think, Sagnik, thank you for that response. I think you bring a very important point in terms of, several global regions looking at the need for rural ambient air quality monitoring. And clearly in India, many things pointed to the need for rural ambient air quality monitoring. But Rebecca or Laura, would you be able to sort of comment on how this might be viewed in Africa or in South America? Both regions, of course, more so in Africa than South America, I think, where you can actually have a similar picture of not a very different rural urban picture, sort of seamless exposures across rural and urban ambient areas. And I guess the monitoring, ground monitoring capabilities in Africa are far lower than anywhere in South Asia, despite the density being equally low in both regions. But I think at least South Asia has somewhat of a superior capacity in ground monitoring networks compared to the African regions. Do you see them as being engaged in, sort of spurring that part as well?
Sorry, just to confirm, with the policymakers in particular, correct?
Yes, correct.
Correct.
Do they see this? Do they see the need to make better use of the satellite data by investing at least modest amounts on whatever is needed to count root or help the modeling process?
Yeah, so I mean, I can speak really only for South Africa. We did in our workshop that I noted last week have some policymakers from Uganda who also were very interested in understanding the potential of satellite measurements. So from the discussions that I've had with policymakers in South Africa, and then with those limited as well with the conference, there's definitely interest, and we can see the potential that this could bring. But it, very much is, I think, many places a discussion of what is possible, what is not possible, what can it be used for, and such like that as well. Also, in South Africa, we do have ground-based monitoring. You can see our dots when people show the global model, the global map of the measurement stations, but we still don't have a lot, considering if you compare it to the US or Europe. And also many of ours are in particular places in urban and industrial areas, right? Because they're for regulatory purposes. We don't really have measurements in, as you said, in rural areas and receptor sites and areas like that as well. And we probably won't ever invest in that because, we have to prioritize where our monitoring stations go. And so they're definitely an understanding outside of where we can monitor and where the atmospheric chemistry will be different. I think a real use, and the policymakers are interested to see what it can be used for. And then it comes to, just communicating what can be used in the terms of uncertainty. But, as I noted, like we do a lot of emission inventory work and there's lots of uncertainties, but, we've gotten quite good at also communicating and discussing with policymakers of what you can use this for, what the uncertainties, mean for what you can take forward and what you can't. So it's just a much more maybe, when you have less information and less of the input information going on, what are the things you can say with this information becomes a very important part of the discussion with policymakers, we found. We're also very lucky in South Africa to have policymakers who are very, also have a scientific basis in air quality. And so we can have the discussions of uncertainty, with that as well.
Yeah. Well, I mean, that's really refreshing to know that the policymakers are, quite scientifically, inclined to have a discussion. And Laura, do you want to comment on?
Yes, maybe just to add something. I think we have a similar situation here in Colombia, as Dr. Rebecca just said, in terms that we have a limited set of ground-based monitoring stations, and especially for those rural areas of the country. They are concentrated in large cities, over 1,100 inhabitants. But we also have an open government and agencies from health and environmental health that are actually working with us in some of the research projects. So they are expecting for results, and for sure they will hear and include those recommendations as part of the air quality plan that is actually running in Colombia for decrease PM 2.5 particularly, and have a better air quality in the country. So I also think that having a robust scientific base of these alternative tools would be an asset for the policymaker to use them as part of the routine policy tools.
Thanks, Laura. Eloise?
Yeah, I see we're close to the hour, so I'll just grab one more question from the Q&A list, and it was a question related to whether or not there are any discussions of having a geostationary satellite like TEMPO or GEMS that is centered over Africa or South America, the two sunniest continents in the world that would provide very, very valuable measurements in the UV. And I open this up to anyone on the panel who might want to comment. But if I were to direct it, I might ask Rebecca to come in and comment, unless anyone else does want to.
So in the question, I actually sent them to your paper, Eloise, a geostationary satellite for Africa. So I, of course, am a researcher in just one country. There's a lot of discussion about it over Africa. And generally, it's the Southern Hemisphere. We all get together and look at that. And there's also, the big gaping holes in a lot of the Southern Hemisphere in general. The South African Space Agency, SANSA, they focus on very small satellites. So I don't think that there would be a large geostationary, of course, from them, but I would hope through a large international effort. And I'm glad that this came up here. I think it would have to be a large international collaboration to get such a satellite up, or at least over Africa, but it could provide a lot of really important information. And Eloise's paper is in the question and answers as well, where she made that point.
Thanks, Rebecca, for raising the profile of my paper. We are coming close to the hour, so I'm not sure if I should hand off to Kalpana or Alison to close us off.
Alison, do we have time for a few closing remarks?
Yes, go ahead and take a couple minutes. That's perfect.
Okay, thank you. Thank you to all the panelists today. I think the session was an amazing exposition of the potential, as well as the complexity of these methods. Clearly, the products that have been developed in the last decade have realized much of the potential predicted in the 2012 critical review published by Raymond Hoff and Sundar Christopher on remote sensing of particulate pollution from space on the occasion of the 50th anniversary of satellite-based atmospheric measurements. Clearly, as illustrated by the applications presented at this session and those that are being developed throughout the global regions, I think we are steadily marching towards the promised land, even if we haven't quite arrived there yet. But in the face of such optimism about these methods, I also want to draw attention to the complexity. I think there is a danger of the complexity being treated naively in some situations. There may be a temptation in data scarce regions to use the products in lieu of investing in improving the input data sets. I think Rebecca alluded to, they probably will never invest on the rural ambient air quality monitoring, but there may also be skepticism or dismissiveness on account of unaddressed uncertainties, and therefore these products might not get fully utilized to their fullest potential. So I think, as Anna Petros pointed out in the last session, capacity building is going to be really, really key to ensure that we are able to iteratively improve and refine both the methods and products. And finally, while doing so, the intended improvements in these products and methods must be strategically designed so that they resonate with national and regional policies. Considerations of scale, ground monitoring, specification, emission inventories, modeling can be weighted based on the regional priorities or the country level priorities to generate optimal products that can inform the health discourse. And I think the two remaining sessions that HEI will host in the series will help us think through such a strategy. Are we pushing the limits of these methods is the next session. So we should be asking, should we be looking at investing in all those areas where the method really can't deliver anymore? And finally, we are planning on a panel discussion to sort of really look at where and how could we use the available data and what could be and will be available in the near future, as Aaron very elegantly pointed out, that could sort of allow us to leapfrog on the health effects research and the burden calculations. So with these few remarks, I join Eloise and the organizers in HEI to thank the panelists profusely for what was an absolute treat to listen to and to sort of really process all this information. And I want to thank the HEI on my personal behalf for this wonderful opportunity to be part of this very distinguished panel and my co-chair Eloise.
So I just want to thank Kalpana and Eloise for their caring, and all the speakers so much for sharing this information, and also the audience for your insightful questions and your engagement throughout the session. This is not the last workshop in the series. This is not the last webinar in the workshop series. There are 2 more webinars that we hope you'll join. And also, for in case you missed the first session or part of this session, all of the slides and recordings will be available on our website soon. As Kalpana mentioned, we'll be having a roundtable discussion as the last session. So please, on any of the surveys, or you can email us with the information on the website, please send us your questions for that roundtable, or the key points that you think should come up. We'd also like to invite you to the HEI annual conference. It's in person this year in Washington, DC, and there are also opportunities to join virtually, and you can find that information and register at the website on the slide. So thank you everyone so much for joining us. And this has been a great session, and I hope we'll all continue this conversation in the other webinars and going forward into the future. Thank you.